Okay, so we discussed the transmission line last time along with the derivation of the telegrapher's equation. So it's pretty straightforward. Hopefully all of you have gone through it again. We finished with this discussion on the terminated lossless transmission line. I thought I'll go through this part again and then go into the next topics and also see some of these responses in the microwave office software as well. Because I think I jumbled up some of these things towards the end last time. So the idea here, and I have already apologized for this, but I'm going to apologize again, but I'll keep doing this. At least for the first 5-6 lectures, maybe 10 lectures, I'm going to keep hammering this point again and again, that microwave frequency intuition for circuits, for structures is very different than what you're used to. Now, it's probably a good thing that most of you never enjoyed electronics in your undergraduate days and probably have not learned much. So maybe there is not much intuition to break, but it's still a very common thing when you think about connecting stuff with wires, two components with wires. It's a very different idea in when it comes to thinking about microwave frequency circuits. Okay, so what we are doing here is there is a 2-port element here. Okay, this is defined as some impedance ZL. L typically stands for load. So that's usually the device on which some signal is receiving. It's again a convention just for you to get used to it. And as I was saying last time, that if you have a resistor in the conventional picture and you attach wires to it, it is still a resistor, right? We don't expect it to behave any differently than it being a resistor. So what's different here is that connecting things like wires is not a benign operation at microwave frequencies, and basically because the dimensions of those objects are comparable to wavelength or even larger than the wavelength of the light, of the frequency of light we are talking about. And again, I will use light and microwave interchangeably because everything is electromagnetic waves, and I will also use electromagnetic waves interchangeably as well. So the picture shown here is that you have this load here, which is some ZL. So it's a complex impedance in general, has a real and imaginary part. Maybe we could write this as something like that. Okay, so R plus J. And connected to it, I mean, here it looks like 2 wires, but these 2 wires represent a transmission line model. And then what we want to understand is, how does this device look like if I connect some other things to these 2 points? So instead of connecting directly at the device where I know that it's an impedance Z of L, if I do the same thing over here with this intervening transmission line, and the transmission line properties are sort of characterized by these 2 numbers here and the length. So Z0 is the characteristic impedance. So remember, it tells you the ratio of the voltage and the current wave amplitudes at any point in the transmission line. Okay. Beta is related to the speed of light, speed of microwaves in this transmission line. It is connected to the inductance per unit length and capacitance per unit length, which a transmission line structure has. Okay, and then the length of this thing, right? So in a conventional picture, you would think that this should not have any effect at all. But here we look at what happens when you connect this thing, and you'll see, and we discussed last time, that it has a dramatic effect. In fact, it can take it completely all over the spectrum of the possible values this Z of L can take. Okay. So how does one actually proceed with doing that? So the first thing you want to think about is, so we are considering this to be sort of a semi-infinite line going in this direction. So we don't really worry about what's happening on the left. And we talk about a wave which is incident into this section, which is basically a section of transmission line of length L and connected to this load impedance. And we just write this as some incident wave coming in. And at any point, again, the ratio of the voltage and the current amplitudes is related to the characteristic impedance. It has to be equal to the characteristic impedance. But at the end, when this transmission line is terminated with this load, then the boundary conditions here are changed. The voltage and the current ratio can no longer be Z0, right? Because if I measure the voltage across ZL and the current through ZL, they should be related to ZL. V over I should be equal to Z of L, right? So that's the boundary condition at this point, which means that the original wave voltage amplitude, when it is coming to the left, from the left, at any point, that is the only wave which was present, right? It's the only one. So the amplitude of that wave, or the amplitude of voltage at any point along the transmission line, is also just the same. So if we say that that was V naught, then it remains V naught everywhere, because there's nothing else happening. Okay, this is the magnitude of the wave amplitude. But at this particular boundary point, it has to satisfy whatever the load you have connected. So the ratio of voltage to current has to be equal to Z of L. So this is again an example of how you deal with microwave circuits which have sections of transmission line and then some device could be on one end, could be on both ends, because within the transmission line, it's all wave equations. And then at the end, it's like normal circuit theory, right? The properties of this Z of L, which we again define this as a lumped element device. Just as a side caveat, the Z of L itself could be a complicated microwave structure, but we are not worried about that. For us, it is defined by the properties at those two terminals, which is right here and here. Okay, we will see this in just a little bit what I mean by that. I can define a ZL, and that is what is going to tell me. And this tells you how to basically solve such a situation. It's very, very similar to problems you have done in quantum mechanics, maybe even in electromagnetic theory, where you have a boundary condition which would set something that, okay, electric field has to be 0. Then you have to impose that, and that changes the thing. So what that means is that in order for this ratio to be equal to ZL, you need to set up a reflected wave component, because in general, the total voltage is given by both the forward propagating and the backward propagating. So again, to avoid confusion, there'll be a lot of repetition of words I will use interchangeably incident wave, reflected wave, forward propagating wave, backward propagating wave, or right going wave and left going wave. This is all with reference to some circuit we have done, but usually we always, as an example here, we consider left to right as positive and right to left as negative, but it's just a pure convention. But this is how most of the circuits we'll be discussing in this book is going to be like. Okay, so the voltage in the general voltage at any point is given by this equation 2.34a, and then the corresponding equation for the current is given. You have seen this last time. So you see that the voltage waves get divided by Z naught, and you develop a negative sign here. And then you put this into the boundary condition, which is that Z of L is equal to the voltage at Z equal to 0, because we have defined this at Z equal to 0. So you calculate V of 0 and I of 0, and then that just simplifies because the e to the I, j, beta factors all go to 1. So you get V naught plus V minus from this equation, so these two terms. And then you get V naught minus V minus from these two terms. Okay. And there is a Z naught which comes here because the I has 1 over Z naught, so the Z naught goes over here. So this basically now tells you the relationship between Z of L, Z naught, and the incident and reflected waves. But what we are really interested in, because ZL and Z naught is all fixed, and V naught plus is what we have imposed on it. So this is really an equation for computing the reflected wave amplitude, which is this V naught 0 minus. And that is just given by this factor ZL minus Z naught over ZL plus Z naught into V naught plus. Now again, this form of expression, R1 minus R2 or R1 plus I2, is something you have seen a lot in like voltage dividers and other things before. Here it's in the context. So remember that all of this in general is complex. So Z, L, and Z naught could be complex, but almost always we will be dealing with transmission lines with characteristic impedances which are real. Because transmission lines with complex characteristic impedances are not very useful. in most cases. So we will not be dealing with that. But Z of L, of course, can be anything. It can be real or complex. Okay. So now we define an important quantity, and this is sort of going to come over and over again, is what we call the reflection coefficient, gamma, which is the ratio of the incident wave, the reflected wave to the incident wave at a particular plane. Here, this plane is Z equal to 0 in this one-dimensional system. And that's given by this ZL plus or minus Z0 over ZL plus Z0. So it's easy to now compute how much will be the amplitude of the reflected wave if you have given a ZL and Z0. Right? So obviously, if ZL is equal to Z0, this number goes to 0 if ZL is equal to Z0. And that is what we usually call as a matched condition. Right? So the wave which is propagating along the transmission line reaches a matched load whose impedance, and again, because I said that the characteristic impedance is always real, so this has to be a real impedance. And then in that case, you get no reflection, which means the entire wave which propagates from left to right will get absorbed at that particular boundary and nothing will come about. So the reflection coefficient is often a measure of seeing how good a match you have in a particular situation. And the reason this is so common and so important is that in general, a microwave circuit or a microwave network will have lots of connections between cables to your devices. And this number basically tells you how good that connection is. Because every time you connect two cables, so again, this is something in the conventional sense, if you're doing a breadboard circuit and you do not have a long enough wire to go from one end to the other end, you just take two wires, either solder them or just twist them, and that's perfectly fine, right? What could be the problem there? That the two wires might have some contact resistance, but that's going to be insignificant compared to the resistance of the rest of the circuit, so you don't really worry about it. You cannot do these kind of things in a microwave circuit. So again, I'm going to be interspersing these with some practical aspects and knowledge as well. So if you have a short cable and you can't like cut it and connect it with two wires, it will just not work, because that is not going to be a well-matched situation. The reason is you need the structure of the transmission line to have that well-defined form, which gives you the correct inductance per unit length and the capacitance per unit length. So if I have one transmission line here and another transmission line here, just connecting it with some wire like this is going to change that transmission line. So this might be Z0, this might also be Z0, but this part here is not going to be. So that automatically means that you're going to get reflections, and that means that you will not get powers going without reflections on either side, which is what you're trying to do if you're trying to make a longer cable. Okay. So okay. Anybody recognize this person? What's the problem? Let me see. Who is this? Let's continue while the person responds. Yeah, so you cannot do these kind of things, and usually there are special devices which enable you to connect one cable to the other, and they try to ensure that these waves don't experience any change in this impedance. So this is not very different in the context of light when you start thinking of light going through different mediums. So you want that refractive index to be exactly the same. Otherwise, you will go to get some reflection at that particular point. And here is a practical information that it is extremely hard to make such connections. You cannot, there's nothing like a perfect connection at all, where you have absolutely zero reflection. So it ultimately boils down to knowing how much of a gamma is tolerable. Right? And this again depends on whether your goal is to deliver power to some device, or whether your goal is to control some impedance very precisely, So then these tolerances become very, very different. So you need to have a sense for what is happening under different circumstances. But this gamma tells you is very important information. Okay. Now this reflection coefficient gamma, which is more precisely the voltage reflection coefficient. And this is again, I'm emphasizing because these quantities often are expressed in different units. So we're going to go through a few of these right now. So when something is mentioned as a voltage reflection unit, it's different than a power reflection unit, which is square of that. And you will see these in different forms in various instruments or in any books or literature you're looking at. So one thing they've computed here is the time average power flow along the line at any point. So they're saying that if you have a general situation, which is we define that you have a transmission line which is terminated by some load ZL, then at any point, how much power is flowing? Okay, and this is sort of like similar to calculating the Poynting vector in electromagnetic theory, if some of you have taken those courses. This is a much simpler version of that. It's one-dimensional, and we're just talking about voltages and currents and not about electric and magnetic fields, though they are all interchangeable, right? Because between two plates, if I have a voltage difference, I have an electric field gradient between them. And there's this current flowing through the wire, then I have magnetic fields in this thing. So this connection between the electromagnetic picture and the transmission line one-dimensional picture, we have not discussed in detail yet. We will do that in one of the upcoming classes so that that aspect is clear. So it basically is the real part of the voltage into the complex conjugate of the current. And so that's like V into I sort of power. Factor of half, you go through the calculation and you get this 2.37. What's going on? See, this is what worries me. When I say please identify yourself, they never do. So why? Oh, was it Gaurav trying to join again? Okay, now for some reason this has frozen. What's going on? How long has this been frozen?
I think it got frozen like 2 minutes or 3 minutes ago.
Okay, when Gaurav, why are you connected twice?
So I had to join again.
Oh. So maybe it was him with a different name. How do I do this now? Some network issue going on. It's weird. It still thinks it's sharing some content. Okay. All right. Okay. So yeah, 2.37, which is the average power. And if you think about it, what is the average power flowing along one direction? It's the power flowing in one minus the power flowing in the other direction. And that's basically what these two terms are. If you look at this part here, this is basically related only to the V0 plus squared. right? So that's the power going in the right direction. And the part which is here is that quantity multiplied by this gamma square. So remember, the voltage reflection amplitude was the incident voltage into gamma. So the power is that squared. So that's why you have this 1 minus gamma squared here. Okay. And this is often, this is the most common way it is expressed, is as the return loss of any interface or a device if you're talking about a particular termination which you have put at the end. So this is the most common thing you will encounter, which is return loss, which is defined in log units. So it's written in dB. So it's minus 20 log mod of gamma. Okay. So remember that gamma can have a positive or a negative sign depending on the whether ZL is greater than Z0 or less than Z0. So we can't put a negative number inside a log. So you take a magnitude and log multiply by 20. And then there's a minus sign because that's the convention. So the return loss is defined as a positive number. But for any finite reflection, gamma is going to be less than 1. Right? Gamma, maximum gamma is V0 plus equal to V0 minus. So it's going to be less than 1. So the log of that number is going to be always a negative number. So you just put an extra negative there. And you, so I forget why this is 20. I think this is some convention people have used. Yeah, it's basically, it would be 10 log gamma square, which is the same as, but even the 10 factor, the multiplication is sort of a convention. But this is important, remember, because there are lots of usual expressions which are used in the context of discussing microwave circuits. So so here, if you look at, for a matched load, gamma is 0. So the return loss is actually infinity for that. Okay. Which is for one of the cases you will be encountering. But when I said that there is no perfect matching, so you will never have a situation in reality which is minus infinity. Of course, in calculations and theory you can have. And if you have full reflection, then gamma is 1 and the return loss is 0 dB. Right? And then you can have values in between. So one example of a figure of merit which is often used is a return loss of 20 dB. So you say that if your return loss is 20 dB or less, it is usually considered a good match. Right? Now let's qualify this good. What does it actually means, right? So 20 dB here would mean that your power is 1%. If I come out of the log units, it's 1%. Because it's 10 to the power 2 square is the 1 over that is the amount of reflection you're getting. So you say that only if less than 1% of the power is reflected when a signal is coming on a cable and either going to a different cable or terminating at a device, you would say that's pretty good, right? 99% of the power is delivered. But again, this is a convention. And I want you to think about how much the characteristic impedance, the load impedance has to change, or how much it can change if you had a characteristic impedance of 50 ohms, which is the most standard system we use for most microwave circuits. How much can the R change in order to remain within this 20 dB limit? So let me just elaborate again. What I'm asking is that you have a transmission line of Z0 and it is terminated with some resistor R, which is close to Z0. If it was exactly Z0, you have 0 reflection. So I'm saying, how much do you need? Like how much can R vary in order for the reflected power to be less than 1%, which is sort of this figure of merit we just mentioned. That turns out to be roughly between 50 to somewhere between 40 to 60 ohms. If you do the calculation, so remember what you want is R minus 50 over R plus 50 square has to be less than equal to 0.01, right? So if I put 40, then I have 10 over 90, right? That's just about 0.01. And if I go the other way around, if I go 60, then I have 10 over 110. So roughly 40 to 60 ohms would give you a power mismatch which is less than 1%. Now, if you compare these two pictures, that, oh, it's only 1% reflected power versus plus minus 10 ohms of variation on 50 ohms, they look very different in terms of how much change we are talking about, right? 1% sounds like a very small number, but 10 ohms on 50 ohms is a 20% variation. Okay, so this is connected to things which will come later, but this is the point I was talking about, that the figure of merit really depends on what you're trying to do. From the perspective of power delivery, this is absolutely fine. It's a 99% power, I'm happy with it. In some cases, even that is not very good. For example, in high power situations, for example, in a radio station, right? You are trying to transmit radio waves and you want to transmit over kilometers distance, maybe even larger, right? How does the radio transmission work? So the waves come and it has to go to an antenna, which then radiates. So the antenna plus the three-dimensional space can together be thought of as a load, because the wave which is coming along your feed line has to basically be absorbed by this. You would like the ideal situation that every bit of power which comes in is radiated out, but that cannot happen. You try to make it as good as possible, but there will always be something which will reflect back. Now, if this, you're talking about huge amounts of power to be radiated so that the signals can reach, then the amount of power which is reflected can actually be damaging to whatever is actually generating those waves. So that power can go back. So there are actually special devices which prevent the signals going in the reverse direction from actually reaching the source of the signals, and they actually send it to another place and where it's safely dumped. So here, even the 1% of a large number could be a significant amount. So these are just examples where, you know, the context really depends. So, but this idea of return loss being 20 dB or less is valid for most typical scenarios. Okay. So one other point here, and then we will look at the what happens actually to the impedance, is again another quantity which is often used to define the amount of reflection that takes place, and that is called the standing wave ratio. Now, if you look at the expression for V of Z, which we had calculated, and you try to look at the magnitude of it along the wave, along the transmission line, you will see that it's not a fixed amplitude. So remember that at the terminal Z of L, it will have some amplitude, but the incoming wave has a different amplitude. So now reflected waves coming, and this is what standing waves do, right? So you have standing waves because you have both forward going and backward going waves. So if you look at any particular point in space and you see how much the voltage oscillates in time. So this is the amp. Remember that the time part we have thrown out of this picture so far, but these are all harmonically varying signals, right? These are microwave frequency varying signals. So if somehow you could measure the voltage or calculate the voltage at any point in space along this transmission line, it will oscillate with a certain amplitude, but that amplitude will change from location to location. Why is that? It's because of the interference between the waves going this way and the waves going that way. And if you had a perfectly matched situation, then of course there is no reflected wave, the amplitude is constant. If you had a perfectly reflected situation, which means gamma equal to 1, then the forward wave and the backward wave have the same amplitude. So remember that V0 plus is gamma into, V0 minus is gamma into V0 plus. So the reflection is perfect, which means all of it reflected. The two amplitudes are equal, which means that they can constructively interfere to give you twice the amplitude or destructively interfere to give you the zero amplitude. So in which case you will have the maximum variation as you go from one place to the other. And this is what is called as the standing wave ratio. So this ratio of V max, which is basically going to be given by the the incident wave amplitude into 1 plus gamma. And then the minimum is going to be V naught into 1 minus gamma. And you can see that this agrees with the intuition we just had, that if gamma was 0, Vmax and Vmin are both equal to V naught plus. And if gamma is 1, then Vmax is twice of V naught plus and Vmin is 0. So this SWR, or more commonly known as the voltage standing wave ratio, because again, this is talking about the amplitudes, is again a quantity which is used to define or characterize how good a match is. So when you look up a data sheet of a particular device, which is say supposed to be, so often one of the things you buy is a 50 ohm resistor, which is called a 50 ohm matched load, but it is never exactly 50 ohms, and also the enclosure and all of those things affect the reflection of how the power couples to that resistor. Then you might find that it is given a specification either in terms of return loss or in terms of VSVR. These are the two are interchangeable because they both only depend on gamma, right? So this is just 1 plus mod gamma over 1 minus mod gamma. And you can see again that when gamma is 0, VSVR is 1. So the perfect match case is that of VSVR equal to 1. And if gamma is 1, then VSVR is infinity. So the larger the magnitude of VSVR, the worse the matching is. So again, this is just for you to get used to these terms, because you will see them in various things related to microwave frequencies. Yeah. So now coming closer to the real part of what we were discussing is, you can now also calculate this reflection coefficient at any point along the line. So let me go back to this figure. So far we have been just talking about the situation where you have what is happening at the boundary of the transmission line and the load. But what we really want to know is, how do we think about the device when we look at it from some point which is further away from it? So that can just be done by looking at the voltages and the currents away from that point. Using the wave equation, you can now extrapolate what those values will be. So this is telling you that the reflection coefficient gamma of 0 at z equal to 0, which is what we are calculating, as you go away from it, varies with this phase factor e to the minus 2j beta L. And of course, if gamma is 0, then doesn't matter, the whole thing is always 0. But the moment gamma is finite, then this gamma of L is actually changing with length, right? Changing depending on where you look at the this particular quantity at. This can also be thought of as, let me now draw this here. So this is z equal to 0, and this is some point z equal to L minus L. We first computed gamma of 0, which is telling us the impedance mismatch between Z0 and ZL at this particular point, right? When I move here, I have now an expression for gamma of L, which means I'm really looking at, and remember that this thing is continuing here as well, right? This is also still Z0. So I have drawn sort of an imaginary line here, and I'm saying I'm going to look at what is reflecting at this imaginary plane. That's what this gamma L means. Okay, slightly subtle concept, which will get clearer when we look at it in an alternate way. But that's what this quantity is calculating here. But this whole thing can be thought of by saying that I will just now make this whole object, which is my impedance Z of L, plus a section of transmission line of length L and characteristic impedance Z naught, and call that now a new effective load, right? So this point here, I can now say there is now a new ZL prime, which is equivalent to this box. And I'm going to now compute gamma for that. And what is the gamma for that? It is Z naught, it is ZL prime minus Z naught over ZL prime plus Z naught. And that is the whole idea of this analysis, is that because this changes, it basically means that the impedance we see at any particular point. So this Z in is essentially the impedance seen at this particular point, or it is equivalent to this new effective device, which is the original load plus the section of transmission line is going to look like. And that again is nothing but the voltage at that point, V of minus L over I of minus L. And you put these numbers in, and you come back to this expression, which we had seen last time also. It is fairly complicated looking, but the point is that this new effective Z of N, or we want to call it ZL prime, depends on, of course, all the existing quantities which are composing this circuit, which is the characteristic impedance Z naught, the load impedance Z of L, but it varies with length in this weird tan fashion. And you know that tan goes all the way from minus infinity to plus infinity. So this expression can go all over the place. So this is what I meant by an extremely dramatic difference. Yeah. Just at the? No. So the specific example of the power calculation which was shown here was done at any arbitrary point. See, it's of Z. So this is, I guess I forgot to emphasize there that the power flowing in one direction, effective power flowing in one direction at any point is actually fixed, right? It has to be fixed. You can't have power building up in one location. So the average power flow is independent of Z, because this expression here is independent of Z. Because the power going this way and the power going that way has to be a fixed number, which is ultimately the power that is being delivered to the load. Because remember that the transmission line we are assuming are completely lossless. So the power cannot disappear somewhere. So that's why this quantity here is independent of Z. When you actually do the calculation, you'll see that the Z goes away. Is that clear? So this is what I meant by the fact that by just connecting, notionally 2 wires or a piece of transmission line, you can completely change what that device looks like at the end of the transmission line. And this is a very unique and also an interesting property, which allows you to do very lots of interesting tricks in order to work with microwave circuits. So we will look at some of those now. But maybe this is a good time to take a look at the microwave office simulation. So let me stop this. Wait. One second, just checking the password for this thing. So imaginary part of the reflection coefficient the best way to think about these complex numbers is in the polar form. So instead of thinking of real and imaginary part, what you want to think about is the magnitude and the phase part. So whenever there is an imaginary part and a real part, it basically means that the reflected wave has a specific angle or phase difference between the incident wave. So what it means is that you can, so if I look at some extreme examples, when you have an open circuit, which means ZL is infinite, then gamma is infinite minus Z naught over infinite plus Z naught. So it's 1. So in that case, it's real 1. So the return wave has the same phase as the incident wave. And you can see that that needs to happen because at the open end, the voltage will be maximum, right? It will be the same voltage whatever came in. The opposite will happen if you have a short circuit. Now gamma is -1. So that can also be thought of as the extreme case of a phase difference of 180 degrees. Now the reflected wave has the opposite phase of the incident wave. And then all other numbers, complex numbers, which have magnitude 1 or less and have some phase factor, cover everything else. That now the reflected wave might have a different amplitude and a different phase as well. So it will depend on the value of the load. So if the load is complex, then you will get complex reflection coefficients. Okay, so let's look at this. So hopefully most of you have started playing around with this software as well. So I won't spend too much time on explaining what I'm doing. So I'm going to take a coaxial line. I'm going to use this simple form. It's called the electrical form, which allows me to define the characteristic impedance, which remains 50 ohms mostly. And the combination of this frequency F0 and the electrical length basically allows me to specify the length of the transmission line. Right. Then I'm going to take. So
are you sharing your screen, sir?
Oh, sorry. I forgot to share this. 1 second. This hybrid thing is very confusing. I'm in so many different computers right now. All right. Okay. Can you see now? Gaurav?
Yep.
Right. So here's your transmission line. I'm going to now take a lumped element for now. Use a resistor. So this is going to be my load. So I'm putting it on one end. I have to put a ground. Then finally, I put a port here. So as I was explaining, this port has various meanings in this context. You can think of that as the source from where the signals are generated. It's also the place where the signals are measured. So any measurement we can do on this circuit is related to this point here where the port is connected. Okay. Now, because I've been going on and on about wires and things and that having a different meaning in microwave frequencies, but these red colored things which are connecting two terminals, they have no meaning. They are basically zero length wires, even if they are finite length in this diagram. Okay, that's just for drawing purposes. But this piece of transmission line has a meaning in the sense that it is defined by these particular properties. Okay, so I'm going to make my reference frequency as 6 gigahertz. For some reason, the default frequency here is set to megahertz. Strange. I'm going to start with a 0-degree electrical length, which basically means zero length. So let me maybe take a minute to explain what does an electrical length mean. It basically is a way to represent the length in terms of the phase that is accumulating. So remember this e to the I beta z factors which had come, that basically tells you that the voltage wave will develop a phase as you go along the transmission line. So this is basically telling you that in degrees. And the convention again is that when you go one full wavelength, it is 360 degrees. So 0-degree means it is basically not there. So then my port is measuring directly on this particular load. Okay, so let me also give this some value of 10 ohms. And the Z equal to 50 ohms tells me that I'm measuring in a system whose characteristic impedance is 50 ohms. So this is the same as saying that to the left of that imaginary boundary I had made, that was still a 50 ohm transmission line. So right now the imaginary boundary is somewhere here. Okay, so this here is the imaginary boundary with respect to what we are measuring. And again, in this context, this point and this point is actually the same points because they're just connected by this red wire. Okay. Now I'm going to define the frequencies over which I want to do the measurement. So we will go a fairly large sweep so that we can see how this thing changes with frequency. So I'll go from 1 to 10 gigahertz. So that's done. And finally, I have to set up the measurement I want to do. So I make a graph first so that it can be plotted. And then I add a measurement. I choose the source, which was the schematic one. And remember that we have not really discussed the port parameters formally, but essentially this is the quantity you have to measure. There's only one port, it is labeled 1. And there's only one quantity you can measure with a single port, and that is a reflection coefficient. And that in this context is called 1,1. So S11 is the same as reflection coefficient. It is actually possible in the simple case to actually go to this part linear and choose gamma here. I don't remember if it is still there, but okay, yeah. We actually want to choose this quantity Z of in. Remember, we are trying to look at the impedance, but we can also look at the reflection coefficient at that point as well, because the two are connected to each other. And I'm going to plot for now the magnitude of this impedance. Okay, so I've defined. So what the software is going to do is it's going to take this point and plot how does this entire circuit looks like at this particular point. And then we will study this as a function of the length of the transmission line, which currently I have set to 0. So let's run this and open the graph. So x-axis is going from 1000 megahertz to 10,000 megahertz. And it's saying a value of 10. So Sulagna, does this make sense? It's saying it's 10 ohms everywhere. So why is it 10 ohms everywhere? No, it's not impedance matched, right? This is 10 ohms, this is 50 ohms. But what is being plotted? We are plotting the effective impedance at this point. But right now, this transmission line doesn't exist mathematically in the model because it's set to be zero length. So which basically is the same as saying that I have connected this point directly to here. And you can see that if I do this, it's going to give me the same result. So we have basically done a trivial case where we're just saying I've connected directly to a resistor of 10 ohms and I'm saying what is the value of that resistor. Now, this resistor which is defined here is an ideal resistor. So when I say 10 ohms, it means it's 10 ohms at all frequencies. It has no frequency dependence. Again, in practice, no such resistor exists. You cannot make a resistor whose value is 10 ohms, which is all the way from 1000 megahertz to 10 gigahertz without any variation at all. Okay. So that's why this is right now doing absolutely nothing. Okay. So now I'm going to change the value here. So I'm going to put a tuner. So that means I can basically sweep this thing using this tool here. Okay. So it has these lower and upper bounds. So I should set the lower bound to 0 because you can't have negative lengths here. And I'll set this upper bound to 360 because that's one full wavelength, right? And we will see later on what happens for larger wavelengths. So as I sweep this now, I've stopped at some point. Remember what it's plotting? It's plotting Z of in magnitude. Okay. And a 10 ohm resistor can look like a 260 ohm magnitude of impedance at this point, which is basically exactly at 6 gigahertz. And then it comes back down here as well. Right. Now, this frequency axis, remember that so far in all the analysis we just looked at, we didn't really talk about the frequency. We're talking about changes in length, right? Frequency was assumed to be fixed at some value, but everything depends on actually the product or the combination of the length and the frequency, right? So this variation can also be reinterpreted as a variation of the length of the transmission line. Why is that? Because for a fixed physical length, different frequencies will correspond to different electrical lengths. Because how much? Because remember, electrical length, I said one wavelength is 360 degrees. But how much is one wavelength depends on the frequency at which you are operating. If your transmission line is of a fixed length, but this is sort of an artificial situation where the transmission line's length is always 90 degrees at the frequency which is defined here at 6 gigahertz, but not at other frequencies. Okay. So at 6 gigahertz, it's exactly 90 degrees, but at other frequencies, at lower frequencies, the wavelength is longer. So the electrical length will be effectively shorter. And at higher frequencies, the electrical length will be larger. Okay. Now, if I allow this electrical length to become larger, then you see this whole pattern just repeats. It's periodic in this thing. So when you connect a transmission line of a particular length to a device, to some load, the effective impedance can vary wildly from its original value all the way to some other values. Now, let's actually look at these. Instead of looking at the magnitude, we will look at the real and imaginary parts. Okay. And in order for it to be simpler, let me make this go back to this 90-degree length. So remember, we saw this maximum value happening here, which was basically at 6 gigahertz. So you can actually see that by adding a marker. Yeah. But exactly at this point, the imaginary part is 1.2 10 minus 9, basically it's 0, right? So this impedance transformation, which is happening, so I've used this term for the first time because essentially you can think of what this section of transmission line is doing is it's transforming the original load into a new load which has both real and imaginary parts. Remember, you started with only a real load here, 10 ohms, real, right? This is a resistor. But by changing the length or frequency, you can create both real and imaginary parts of this at that particular point. And again, this is not so surprising. It's because now the reflected waves will come at various angles, and then that will determine what is the ratio of voltage to current at any particular point, and that will automatically give rise to real and imaginary parts. But there are special lengths where the imaginary part can go to 0, and this actually plays an important role because this particular length at that particular frequency, remember that the circuit here, so this part can be a little confusing because of the way the convention is. The definition of the transmission line is with respect to a particular frequency. So this actually means that it's a fixed physical length, and it's defined by saying it's 1/4 of a wavelength, 90 degrees at 6 gigahertz. Okay, and at that particular choice, your imaginary part of that new impedance or the transform impedance goes to 0. So you can think of this section of transmission line as transforming a 10 ohm resistor into a 260 ohm resistor or 250 ohm resistor. But exactly only at that frequency. This happens only at this frequency. So remember, as the moment we go away in frequency, it's a different value. Maybe let's pause here for a second because I can see lots of very puzzled expressions all over the place.
I couldn't realize the number just and real part and the imaginary part, the maximum number, because here I think at 90 degrees there will be tan beta infinity. So Z should be approximately Z0, right? Sorry, Z10.
So you actually try to calculate that value. So the I will come to that in just a second, but in order to calculate that correctly, you have to take the limits in the proper direction. You cannot just put infinity and do it because you get some infinity over infinity kind of things. So you have to take the limit in the right order. We will come to that in just a second. Any other questions? Doubts? Two different aspects here is going on. Okay, first, let's think only at 6 gigahertz because the transmission line is defined with respect to a 6 gigahertz. That's just a convention for defining. So instead of saying that it is of a certain length L, this definition in terms of frequency and electrical length is equivalent. It's more sort of generic, right? At that particular frequency and for a length of 90 degrees, I get a new impedance from a 10 ohm impedance, which looks like having a real part of 250 ohms and an imaginary part of 0 ohms. Okay. What I'm saying is that the other frequency, the behavior away from this point can be interpreted in two different ways. You can think of them as a change in frequency for the same physical length, or you can consider this as a change of length at a fixed frequency. But I can also change the length at this particular point. So let me do that. Yeah, in fact, this is basically 90 degrees, right? So let me actually tune this here. Allow me to tune the frequency as well. And let me freeze these traces so that they stay there. If I now change the definition of the transmission line, which was defined as 90 degrees at 6 gigahertz, and instead make it 90 degrees at 5 gigahertz, you see what has happened? That peak position has just shifted to 5 gigahertz, right? This is exactly the same. It's 250 ohms, but now it's at 550 gigahertz, and this is 0 ohms at 5 gigahertz. So this length is special, right? As he was saying that, you know, the tan beta L, the beta L goes to pi by 2. So this length, which is a quarter wavelength, is special, and we will discuss more about that in a second. So here, by changing the length, I have gotten this thing to happen at 5 gigahertz instead of 6 gigahertz. But I could do something here. I can now change the length in such a way that it goes back to 6 gigahertz, right? So what is the transmission line now? It's defined as a 75-degree line at 5 gigahertz, but 75 at 5 gigahertz is the same as 90 at 6, right? Because if you take the ratio, it will come out to be in the same way. This is 75, right? Yeah. Because 5,000 is 75% of, sorry, 75 over 90 of 6,000. Yeah.
So if I have an access mobile,
Sorry, you have to speak a little louder.
so but like whatever analysis we've done till now, we haven't brought up omega. We just assume that this video is similar.
Earlier, yes.
So like how do we go on the writing expressions if we want, if it all want?
No, so omega is inherently present in those expressions in the form of beta. So beta is related to omega. So depending on the frequency at which you want to calculate, you calculate that corresponding value of beta. So that's why it's like combining wavelength and frequency together, right? So that will give you a constant thing. So if you have the frequency, or equivalently, if you have the wavelength, and then you have the actual physical length, so it becomes like a ratio of length, it becomes a dimensionless number. So that ratio will change, which is exactly what I just demonstrated, that the response at 6 gigahertz for a transmission line which is defined as 90 degrees at 6 gigahertz is the same as the response of a transmission line which is defined as 75 degrees at 5 gigahertz, because there is no difference between these two definitions. 75 degrees at, so this object here has exactly the same properties under these two circumstances, because it's just two different ways of changing. It's like whether you have changed the beta or you have changed the L, but the product beta L has remained constant. That's what's happening here. So why is this kind of circuit useful? Because it allows you to change the impedance from one value to the other, and that can come in handy when you're trying to match certain things, or you're trying to deliver power from a source which maybe has a characteristic impedance of 50 ohms, but you want to deliver power to a load which has 10 ohms, but you want to maximize that power delivery. But the catch is that you can only do it over a narrow range of frequencies. Okay, and this is another thing which will come over and over again, most microwave circuits have a narrow band of operation. Remember that this only looks like an exactly 250 ohms at exactly this one frequency, right? The moment you deviate from that frequency, you start developing some imaginary parts. But usually, again, there is a tolerance or a figure of merit, and you will say, okay, as long as the power delivered is within some number, I'm okay with it. Or as long as the impedance is within some range, I'm going to call it okay, and I'm going to call that device a functional device.
So, is it not possible to make it more flat? Currently, in lump analysis, I don't think it is possible, but are there other ways to make it flat?
That's a very good question. Let me just elaborate on the question. So what does it mean to be flat here? That you would ideally like that this real part remained close to 250 ohms over a larger range of frequency, and the imaginary part remained close to 0 over a larger range of frequencies. But what is it that is determining this shape in the first place? Like how quickly it is falling off? What is determining that? That depends on the transmission line's properties itself. This, I can just say that, so this particular thing is called a quarter wave transformer or a quarter wave impedance matching circuit. That by definition will have a certain fractional bandwidth. What do I mean by fractional bandwidth? That it depends on the center frequency at which you are operating. So often you will hear or see things like 10% bandwidth. It means that it is considered matched within 10% of the ideal frequency, which in this case is 6 gigahertz. But as you move that frequency along, the absolute bandwidth will change because it's always related to the frequency at which it is designed for. So in order for you to have a more flatter response, you cannot just use a single quarter wave transformer. You need to do something more sophisticated. And maybe we can see an example of how that would work, right? So I was basically asking you, what is it that determines this match, right? This depends on the transmission line and also the impedances you're matching. Yeah, question.
So it's a quarter wave is special because we're using 90-degree and getting peak is 6 gigahertz. So similarly for 75-degree, we got it 5 gigahertz. So why is this quarter wave like special? Because we're getting same response at 75 degrees as well.
Because it was 75 degrees at a different so when I so currently the transmission line is defined as 75 degrees at 5 gigahertz, but that is the same as 90 degrees at 6 gigahertz. That's why this peak is at 6 gigahertz. If I make the length 90 degrees at 5 gigahertz, it has shifted to 5. So by special, the reason it's special is that it's the point where the imaginary part goes to 0. So a real, because you remember you started with a real resistor 10 ohms, and it has transformed into another real resistor of 250 ohms. That's why I mean by special, because when you talk about impedance matching, you want the imaginary components to be not there, because then the power, you'll always get reflection, because your transmission line is a real. So maybe I should elaborate. What do I mean by that? Remember, gamma is ZL minus Z0 over ZL plus Z0. In most practical cases, Z0 is a real number, which means gamma equal to 0 can only be obtained if Z of L is also real and equal to Z of 0. So that's why we want to, when you want to transform an impedance match to a real circuit, you would want an impedance transformer which does not leave or create an imaginary component of the transformer. That's the special part. But depending on which frequency you're operating at, you will have to design the transformer for that frequency.
That's what I'm saying. Like at 75 degree 5 gigahertz, also the imaginary part is 0.
Yeah.
So that's a constant. Like 90 degree of 6 gigahertz, that then also we're getting imaginary part 0 and at 75.
But at different frequencies we are getting now. So if you want to do an impedance matching at 6 gigahertz, you will design it to have 90 degrees at 6 gigahertz.
So we are fixing this because of 6 gigahertz.
That's right. So which frequency the matching is happening is a choice you make depending on your needs, right? You are going to, your circuit or whatever you're designing is going to have a special frequency of operation. So you will have to design it for that.
So if it's from the beginning, that you want-
Yeah, that is defined by your requirements of what you're trying to do. I mean, right now I'm just trying to change these parameters to show you what happens at these various things. Okay, so there are a few open questions here. And the first question is, so first thing we said that, okay, the choice of frequency is fixed. But why is this 250? Where did that come from, right? It was 10 ohms in the beginning. Why is it 250? All right. So let's see if we can change something else. If we go here, remember that this is the transmission line we have control over. Everything else is fixed. This 10 ohms is fixed. This is our 50 ohm system. So I have one more quantity which I can play with, which is the characteristic impedance of the transmission line itself. Right? What happens if I do that? Oops. So let me clear the graph. Let me go back to 5 gigahertz is fine, I guess. So right now I'm working with the 5 gigahertz quarter wave section. So 90 degrees at 5 gigahertz. And I'm going to freeze this. And I'm going to change the characteristic impedance of the transmission line itself from 50 ohms. Okay. I have increased it and it's going up. And if I decrease it, it comes down. Right? So the value it reaches, but important thing to note is that the imaginary part is always still 0 at that particular point. So that's why it's special as well, because it's related to an interference condition we'll see later. What changes always is the magnitude here, and something else. Do you notice? That's the value, but what else are you noticing about the curve? It's getting flatter, right? Which means it's sort of working over a larger range of frequencies. Right? If you say that, again, what could be a natural figure of merit for such a circuit, right? You'll say, okay, if I'm trying to match something to 10 ohms, then maybe as long as it's within a few percent of that 10 ohms, I will call it matched. So if the curve becomes flatter, that means that it's working over a broader range of frequency. So one of the things which you asked, the bandwidth for a single, sorry, you were asking about the bandwidth, the single section of 90 degrees, which is basically the quarter wave transformer, depends on how different of a impedance you're trying to match. Okay. So let's look at this in another way. We will go back to this 50 ohm transmission line. Sorry. Freeze it. Now I'm going to change this now. So what do I mean by what we are trying to match? So we are trying to match 10 ohms to 50 ohms, right? These are the two extreme limits we are doing. So you see that if I change that, the impedance, bring it closer to 50 ohms, now it's going towards, then also it becomes broader, right? So we are actually varying things in a very strange way here, because we are not really calculating the actual matching part, right? Which is not seen here. The thing we actually want to do is to make this point, if you want perfect matching, what do you want? We want to make this point look like no? I want to look at 50 ohms because this is 50 ohms, right? So we want this thing, this whole object here to basically be equivalent to a 50 ohm resistor. at some frequency, right? So we need to check that. So let's keep with 20 here, and let's keep with 50 here. And we know it's going to happen at 5 gigahertz. Let's disable the imaginary part for the time being, because we know it's always going to be 0 at that point. And we now want this peak value to be equal to 50 ohms. So we will change, the only thing we have our control now is the characteristic impedance of the transmission line itself. Right? So I'll have to increase the range here. Let's put this marker at 5 gigahertz. So we are at 55. Oh, sorry, I think I changed something wrong here. Sorry, let me just go back. So the resistor was 20 ohms. And I'm going to change the characteristic impedance, which is here. And I want to make that so let's say that's close enough. So what's plotted here is the transformed impedance. It has now become 50 ohms. And what is the value of the characteristic impedance we have obtained? It's 31.8 ohms. So by connecting a quarter wave section of 31.8 ohms, a 20 ohm resistor transforms into a 50 ohm resistor, real to real to real.
That 31.8 is the characteristic impedance of the total length or per length?
Well, a transmission line has only one characteristic impedance. It's the characteristic impedance of that transmission line. What do you mean by per unit length?
How it's defined in the derivation of
but that's the inductance and capacitance per unit length you're talking about. See, Z naught is this, right? Where the inductance per unit length and capacitance per unit length of the transmission line give you that. But that number is uniform across the transmission line. I mean, usually you can design transmission line whose impedances changes with length if you want. Those are also some kind of transformers. But that's what this is for the whole transmission line. So you have to design a transmission line whose value is of 31.8 if you wanted to go from 20 ohms and match it to 50 ohms. But this value depends on the impedance you're trying to match. So one side is always 50 ohms. So that's fixed, right? So let's freeze this again. Now, if I change this 20 ohms to 10 ohms, then this is not working anymore. So I have to adjust the transmission line impedance. In fact, increase the close enough. And now the value is 22.3. So it depends on the characteristic impedance of the transmission line and the load impedance. Both of them are needed to get this to match correctly. The other thing to note, which you should have been obvious by now, that this transformation at this special point is actually completely independent of the frequency in terms of the values you need. So this was all done at 90 degrees at 6 gigahertz. Sorry, at 5 gigahertz. If I make this 6 gigahertz, just the curves will shift, but everything else remains the same. See, this value here is still 50 ohms and it is still 0 here. So this value of the impedance transformer you need. So you need basically two things to define your impedance transformer. One is the effective length. It has to be a quarter wavelength at the frequency which you're interested in. And then you need it to have the right characteristic impedance. So that number does not depend on the frequency. Okay. So just to maybe show you that formula, and I think we should wrap up in a few minutes. Ms. Riji. Ms. Riji, hello. I think is there an asset colloquium today? There is, right? Yeah. So maybe just to again show you the comparison of the bandwidths. So let's go back to 5 gigahertz. So you can already see that the previous one, the one which is in the light part, that was the impedance matching curve for 20 ohms to 50 ohms. The one which is currently drawn is for 10 ohms to 50 ohms. So you can see that it has a sharper fall off. It deviates much faster. So the more mismatched things are, the harder it is to impedance match it over a broader range of frequencies. Okay. And this is also a hint on how you could actually make a impedance transformer. Now, of course, you have to think beyond what we have shown here. How do you make it more broader? Right? The clue from here is that you need to match with less mismatch between the two things. But your endpoints are given 10 ohms, 50 ohms. How can you do it? You do it in steps. So you make first a quarter wave transformer, which will take that 10 ohms to maybe 20 ohms, and then maybe 20 to 30, and then 30 to 40. Now you have to sort of believe me, but play around with this. And I think there is a problem like this in one of the assignments. There is no reason that this should happen, right? Because you're going to now have several curves. Each of them will look broader, but then the total response is the combined response. So it could still become narrower. But it turns out that you can actually do this. And there is a limiting case of way you can think about, because remember, what is your impedance transformer now look like? It looked like a transmission line. As you go closer to 10 ohms, your transmission line impedance will be closer to 10 ohms. It will be slightly larger. So remember that, sorry, slightly smaller. So remember, to match 20 ohms to 50 ohms, you needed a transmission line of 22.3 ohms. To match, 10 ohms to 50 ohms. Earlier, when it was 20 ohms to 50 ohms, it was 31.8. So it's somewhere between these two numbers. He was putting a formula, which I'll show you just a second. So if you do this multi-section transformer, on one side you have 10 ohms. So that the first impedance transformer's characteristic impedance will be something slightly more than 10 ohms, because you're trying to match 10 ohms to 20 ohms. Then the next one will be slightly between 20 and 30 ohms, and so on and so forth. So what's actually happening is that you have a transmission line whose impedance is slowly changing from closer to 10 ohms to closer to 50 ohms. Now you can take a limiting case of this and imagine a smooth variation in the L per unit length and C per unit length, so that the transmission line characteristic impedance itself is changing. So then there are questions like how quickly it can change. So what does quickly mean? Over what length? When it comes to multiple sections of quarter wave transformer, the length is fixed. It has to be quarter wave at that frequencies. So then the number of sections you use will determine how smooth your changes are, and that will determine how broad the bandwidth is. But it also means that the overall transformer length will become very long. So then, in a practical situation, it could be, you might worry that, okay, there are too many sections. In reality, these transmission lines will have losses. So that can affect. So you have to make these compromises to decide which choice to make. And so those things are often called continuously tapered transformers. And in fact, in POSAR, there is a discussion on this, that you can actually find an analytical form for the curve of how Z naught should change from one end to the other end to get a nice match. So how quickly it changes but no, these are concepts you're familiar with if you have studied them in electromagnetic waveguides and all. Like a smoothly changing waveguide will ensure that the waves don't reflect. What does smoothly changing here? Basically, when the dimensions are changing, the L per unit length and C per unit length are changing. So if they're changing in a very slow and continuous fashion, then at every point, the waves will not see a very different medium in front of them, and hence they will not reflect. So in the next lecture, we will begin with this viewpoint of multiple reflections when we have these sections, which will also come back to the same impedance transformer formula. Where I'm so let me just quickly flash that. Yeah. So this here is the formula I was talking about. So what it's saying is that if you have a load L and you have connected a quarter wave transformer to it of characteristic impedance Z0, then at the end of that length L, which is lambda by 4, the new impedance is going to be given by Z0 square over ZL. So the characteristic impedance of the transmission line squared divided by the original load impedance, that is going to be the new impedance. So in the problem we were looking at in microwave office, we wanted that new impedance to be equal to 50 ohms. So ZL was 10 and we wanted Z in to be 50. And then we computed what Z0 was for a few different cases. And this you have to take the limits properly, otherwise that formula will not come out. But we will look at this in more detail in the next lecture. So we'll stop there and take maybe any quick questions. Okay, all right. So regarding Monday's lecture, I'll email you because this room is not available at that time on Monday. And since the class is now reasonably big, that WS rooms might not be very comfortable in general. And plus, I think I had mentioned to you that that place is very moldy and I have allergies. So I might just sneeze away throughout the class if you go there. So I will let you know, I'll figure out how we can do that. All right, so we'll see you on Monday.